Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll continue looking at experimental design and factor in Chapter 5. So we'll jump over there. Here we are in Section 5.2, extending the one-factor design to having multiple factors. This is a very common situation when we're doing experiments, and perhaps one of the most commonly used experimental design is the completely randomized design. We're going to look at an example where we compare different insecticides as one factor and the dosage, low, medium, and high, which is the other factor, to see how that influences survival time of these beetles. So the completely randomized design, what that means is we're going to define combinations of treatments, say insecticides and dosages, and then we are going to take a population of beetles that we have got a sample from, and hopefully those are very homogeneous sample of beetles that maybe all have the same age and the same type or strain of beetle, and then we're going to randomize those beetles into the different treatment combinations. And any inference we get from such an experiment is going to apply to that type of beetle specifically. And if you're going to try to generalize to other types of beetles or other types of insecticides or something, you really either have to do that scientifically by having some other information, or first, some sort of scientific data, or conduct further experiments, which would be my general strategy here. All right, so we're going to look at this two-factor crossed experiment where we've got different insecticides. We have 4 types of those, A, B, C, and D, and we're going to have different concentrations or dosages, low, medium, and high. And this will be a completely crossed two-factor experiment. The crossed means that there's going to be combinations of the insecticides and the dosages, and the completely means that every insecticide has every set of concentrations. Furthermore, we're going to perform randomization such that we have a balanced design. So we're going to start with 48 beetles. We've got 12 experimental groups because we have 4 insecticides and 3 dose levels, so that's 12 combinations. And 48 will divide evenly into 12, so we've got 4 beetles into each group. So that will be a balanced design. Balanced design is often desirable because it means that every group has the same amount of information in it. If the variability across all the treatment combinations is the same, this will give you the most powerful design by reducing the amount of uncertainty in your estimates as possible. All right, so let's take a look at the data for this. So I'll read in the data, create some factor variables. That's what that's doing there. And this is what the data looks like. We've got dose. Let's look at this column first. Insecticides, we've got A, B, C, and D. And notice that it repeats 3 times because we have the low, medium, and high doses. These T1 through T4 are the 4 trials. Each of these is a beetle. So this here is the survival time for insecticide, the beetle for insecticide A, the low dose. The first beetle lived 3.1 hours. The second lived 4.5 hours. Oh, I never mentioned that. The units here is unusual. It's in 10-hour intervals. So 0.3 is actually 3 hours. Okay, that was an unusual choice. But there I have. I've inherited this data set, so I'll just use it as it is. All right. There is 1 beetle here that survived more than 10 hours. We'll need to reshape that wide format data into a long data set by using reshape, melting the beetle, and we're going to want to have the dose and insecticide columns. Sorry, I'm jumping around. The dose and insecticide columns appear for every observation. We just want to take these 4 columns and make them long. So we're going to stack this first column on top of the second column, third and fourth, and so on. And so what we have here is the ID or identification variables are dose and insecticide. The variable name is number. So the variable name is the column that has these labels, T1 through T4. And then finally, these values, 0.31 and so on, their name is going to be hours 10. So we've got this new Beatles long data frame that was created right here, and its structure has dose and insecticide. The number is that basically the beetle number, beetle 1, 2, 3, and 4. George, Paul, Ringo, Paul, and the hours. All right. Different beetles. So here's the first 6 observations of the long data frame. All right. In a 2-factor analysis of variance, which this is, the basic unit of analysis are cell means. So if we look at this table here, we have for the insecticides are the rows, A, B, C, and D. The columns are the doses. So we have low, medium, and high, 1, 2, and 3. And each number inside is the average of 4 beetles. So 0.413 is the survival time, the average survival time of the 4 beetles that had insecticide A at the low dose. One thing you can see right away is that for insecticide A, low dose has the highest survival time, medium and high dose has the shortest survival time. All right. In addition, we have some margins. This margin is for the insecticides. So that basically for insecticide A, we're going to average over the cell means, and those averages gives you about 0.314. So now comparing across the insecticides, insecticide A has the lowest average survival time, and insecticide B has the longest average survival time over the doses. Similarly, for the low dose over insecticides, the average is 0.6 hours, 6.2 hours, and on the high dose, the average is 2.7 hours. Finally, you can look at the grand mean, and whether you average the rows or the column margins, you'll get the same number. One important point here is that we have a balanced design. So there's 2 ways to get 0.314. The first way is just to average all 12 observations that went into all these 3 means. But in general, that's a bad idea, because if you have an unbalanced design where you say you have many observations for the low dose and only a few observations for the high dose, when we care about what the average survival time is for insecticide A over doses, we don't want the condition that had lots of observations to overwhelm the average survival time for that insecticide. So the right thing to do is to average the cell means, which is what this does here. We're going to average over these 3 numbers. Each of these 3 numbers might have different variability associated with them, but so be it. So this is the average over the averages. And finally, this grand mean can also be thought of as the mean of all 12 cell means in the center. So our goal is to understand the structure of these 12 numbers. For example, what we see for insecticide A, when we have long survival time, medium survival time, short survival time, does that pattern hold up over all insecticides? Or is that pattern different? Okay. You can ask the same question looking down the columns. In this case, I think it's easier to think about it over the rows, that for a given insecticide, how does dosage change the survival time? All right. So we want to develop a statistical model that answers that question. So in general, let's do a little bit of looking at modeling in terms of theory. Let's have two factors. So factor 1 we'll just call F1, and I will index the levels over factor 1. Okay, so here's another place to see it. I is the ith level of factor 1. Factor 2 will have J levels, capital J. And K is going to be the number of observations in each treatment combination. So here we've got mu ij. That mu here is going to be the mean for the ith level of factor 1. So maybe that's the insecticide, A, B, C, D. The jth level of factor 2, so maybe that's the dose, low, medium, and high, 1, 2, and 3. And then we have the 4 beetles. Okay, so we have Yij, K. Y is the survival time for beetle K, right? There's 4 beetles, 1, 2, 3, and 4, that undergo treatment I. So that's insecticide I, dose J. Those are going to be centered at the mean, which is from the table that above, plus a residual. That's the error term. And if you look at the variance of these errors, that's the variance around the mean. All right. In all of these cases, we're going to be looking at how can we take the mean for every cell and develop a structure for the mean. So this mu ij is here, and we're going to break this into parameters that we're going to estimate. Mu is the grand mean. So if I page up for a moment, mu is basically 0.48 here is an estimate of mu. It's the grand mean over all insecticides and doses. Alpha I is the effect of the ith level of the first factor, or of the ith factor. So if alpha is the insecticides, for insecticide A, B, C, D, if I page up, so here's the grand mean mu, 0.48. Let's look at insecticide, let's look at insecticide, let's look at insecticide A. Okay, so here we've got 0.314. So alpha 1 for the first insecticide is the difference between the grand mean and this row mean for insecticide A. So that difference is this is the stuff I'm not good at, 0.166. Okay, negative. So to go from the grand mean to the mean for row A, we have to subtract 0.166. That's the effect of insecticide A. Insecticide B is a positive number. Okay? And if you add up all 4 of those alphas, they sum to 0 because they're all centered at the grand mean. So I'll page down. So that's alpha I. Beta J is for the columns. Those are the doses. So if I page up, dose 1, so beta 1, is the difference between the grand mean and the column mean. So 0.618 minus 0.480, that is 0.128, something like that, 0.138. That's the difference. Okay, and similarly, for dose 3, this is going to be a negative number because this column mean is smaller than the grand mean. and the sum of those effects is 0. Finally, there's this interaction, and this is lousy notation. It's sort of old-timey notation. Alpha, beta inside parentheses indicates a single number, not the product of alpha and beta. So this is a single number indicating that this is an interaction between alpha, or between factors represented by alpha and beta. And so this interaction is the difference So we're trying to calculate 0.413. Okay, so we start at the grand mean mu. We add alpha I, which is a negative 0.166, to get up to insecticide A. Then we need to get over to dose 1. So we're going to go from here over to dose 1. And that effect was beta J. That's 0.138. And if you add those up, do you get this number? Probably not. And so that's where the interaction is. The interaction is what remains as the difference. All right, so you know what? Let's see what we get. So we got 0.48 is the grand mean. We're going to add, to get up to insecticide A, 0.166 negative. Can I do that? No. Calculator is a lousy calculator. All right. 0.48 minus 0.166. Okay. Oh, 0.34. That's good. Then we want to go over to the left for dose 1. So what's the difference between the grand mean and this? I'll probably get this wrong, but I think it's going to be plus 0.138. Okay, so now we have 0.452. So the interaction is the difference between this cell mean, 0.413, and this mean, which we would get if the rows and columns of this table were independent of each other. Remember last semester, Chapter 7, Categorical Data Analysis, we have a test for independence between rows and columns. This is similar, except rather than having categorical data, strictly speaking, we have response continuous variable data for each of the cells. So instead of looking at proportions, we're looking at means of numerical data. So the interaction here tells you how different the cell mean is of 0.413 and what you would get as an expected number from the row and the column means. And if these numbers are very different over all the different cells, then that indicates that there's an interaction. And we're going to look at images of interaction very shortly. You know what? I don't want to have to look at that calculator. All right. Let's scroll down a bit. So that is a description of how we are going from our observational data Y, which are based on means. We took the mean and we structured it in terms of parameters, in terms of row means, column means, and interactions. And the hope in almost every case is that for when we test whether there's an interaction or not, so these are parameters we're going to test. We hope that the interaction parameters are all equal to 0, or at least not statistically different from 0, because interaction makes life complicated. So we often test that parameter with the hopes that we can fail to reject the null hypothesis. And that is the case in the, so let me see, it died. All right, yeah, so the interaction model has those interactions in it. We hope often that interaction equals 0, which would leave us with an additive model. where we'd have just the grand mean, effect 1, effect 2, but no interaction. All right. There's ways of calculating all these things. The computer is doing all this for us, so I'm not too concerned. I would glance through. This ANOVA table is how we test the effects. So we've got a test for interaction, which has some number of degrees of freedom. And you may recall this is the same degrees of freedom as we had in the chi-square test from Chapter 7 last semester. Number of rows minus 1, number of columns minus 1, that product. And each of these gives us an f-test, where we are looking at the mean square for that part of the model divided by the mean squared error. And each of our tests have this form where we're asking, are all of the effects of, say, insecticide equal to 0? Meaning, can we just simply describe all insecticides by the insecticides by the grand mean, or not, or by a common mean? Same thing for doses. And in this case, we're going to have I minus 1 times j minus 1, so that's going to be 2 by 3, 6 different interaction terms, and we're asking whether all of those are equal to 0 in the insecticide example. All right, so go ahead and read through that. I want to show you some pictures of interaction. Here is a situation where there is not interaction. All of these lines are parallel. So on the vertical axis we have population means. On the horizontal axis, this doesn't perfectly correspond to the beetle example. But imagine, say, we had 5 different insecticides, okay? That would be these 5 levels of factor 2. Each line represents a level of factor 1. So this middle line is level 1 of factor 1. So just for making this similar to the beetle example, let's let the second level of factor 1 be the low dose, the first level of factor 1 be the medium dose, and the third level of factor 1 be the high dose. So we've got sort of long survival times at top and short survival times at the bottom. So there's no interaction here, these parallel lines, because for a given, basically you can think of it about as being conditional, whether there's conditional dependence or not. So conditional on level 1 of factor 2, conditional on that, how are the levels of factor 1 different from each other? So in this case, the second level of factor 1 is, say, it looks roughly 2 units higher than the first level of factor 1. The third level of factor 1 is roughly 2 units lower, and that's the relationship when we're at the first level of factor 2. Now, is that the same relationship for different levels of factor 2? If it's the same, then there's no interaction. So you can see all these lines are parallel, they come up here, and the differences are the same, about 2 units higher and 2 units lower, and so on. And that's the same regardless of what level of factor 2 is. Now you can see that the mean for different levels of factor 2 is different, right? Sort of medium, high, low, high, medium. But the structure of the differences over the structure of the differences over the levels of one factor does not depend on what level of the other factor we're at. And because there is not a dependence there between factor levels, there's no interaction. and that corresponds to our additive model. Because if we know basically the mean level for each level of one factor, and we know the mean level of the levels of the other factor, we simply add those effects together to get the prediction for the mean for that cell. Boy, that's a lot of words. Let me page up for a moment. And we skipped all those summation signs. Additive model. So here, the additive model, where there's no interaction, we've got the grand mean, we have offsets for one factor, for the different levels of one factor. We have the offsets for levels of the other factor. And adding those together gives us predictions for what we should observe. Now, when there is a dependence, that's where these interactions come in. So let's look at a picture for that. I'll page back down. When there's interaction, anything goes. So you can see how unstructured this is. For the first level of factor 2, let's see, let's use factor, let's look at level 5 for factor 2, because that's where the labels are. Right, so for the difference between, for factor 1, the difference between level 1 and 2 is roughly, I don't know, 4 units or something. And then between level 1 and 3 is maybe, I don't know, 6 or 8 units. Okay? But that is different when we look at level 4 of factor 2, right? In particular, levels 3 and 1 of factor 1 are only 1 unit away or so. And so because there's different relationships between the levels of factor 1, depending on which level of factor 2 you're at, that is interaction. And that basically means that cell means can be whatever they're going to be. There isn't a structure there necessarily, or it's not obvious what the structure is. And so the interaction basically allows us to estimate each of these individual means separately. And yeah, so we often test whether there's interaction in the hopes that we get this beautiful situation of the additive model. All right, let me scroll down. So to keep this video a little bit shorter, let me stop this here, and I'll come back and start with this example of survival times for the beetles, and we'll see how this plays out in the analysis.